In this video, I'm going to cover the combined gas law, which really is just combining multiple gas laws into one gas law. So, what the combined gas law states is that when the amount of gas is held constant, the combined gas law describes the relationship between pressure, which is P, volume, which is V, and temperature, which is T, by combining Boyle's law, Charles' law, and Gay-Lussac's laws. So, the combined gas law reads P1V1 over T1 equals P2V2 over T2. P1 is the initial pressure, V1 is the initial volume, T1 is the initial temperature, P2 is the final pressure, V2 is the final volume, and T2 is the final temperature. Something that you might see pop up that isn't directly related to the combined gas law, but I'm going to put it here anyway. Something called STP. STP means standard temperature and pressure. So when you see that a system is at STP, that means that the temperature is 273 Kelvin and the pressure is 1 atmosphere. If we're looking at kilopascals, it's going to be 100 kilopascals. And if we're looking at millimeters of mercury, it'd be 760 millimeters of mercury. Those are your baseline, like, standards of temperature and pressure that scientists use, and then we just call it STP. So for the first example problem, the volume of a gas-filled balloon is 30 liters and at 313 Kelvin and 153 kilopascals of pressure. What would the volume be at standard temperature and pressure, which is also known as STP? So let's highlight our known variables. Let's pull those variables out. So the initial volume is 30 liters. The initial temperature is 313 Kelvin. And the initial pressure is 153 kilopascals. Our final temperature, since we're turning the system, or we're changing the system to become at STP instead, would be 273 Kelvin, because that's the standard temperature at STP. And then our pressure, final pressure, would be 100 kilopascals, because that is the standard pressure at STP. And then our unknown is going to be the final volume. So we can just plug these numbers into the combined gas law, making sure that all of our units are the same on both sides. So our pressure would be in kilopascals on both sides, temperature would be in Kelvin, volume would be in liters. So when I plug all of my variables into the correct places, this is what I would get. And what's nice about this, yes, there's a lot of numbers, but you're just multiplying and dividing. So sig fig wise, you can just look at how many total sig figs all your numbers have, and whichever one has the lowest amount, that's how many total sig figs you want in your answer. So to solve this, I would cross multiply and divide. So 153 times 30 times 273 would be equal to 313 times 100 times V2. So you do 153 times 30 times 273 divided by 313 times 100. That would give you V2, which if you plug that in, which you should practice plugging that in, please, you would get a volume of 40.0 liters, two proper sig figs, which would be 3, because all of our numbers that were given have 3 sig figs to them. Mathematically, you could plug 40 in for V2, solve for the left side of the equation, solve for the right side of the equation. They should be equal to each other. And that's how you can check it mathematically. For the second example, we have 5 liters of a sample of air has a pressure of 107 kilopascals at a temperature of negative 50 degrees Celsius. If the temperature is raised to 102 degrees Celsius and the volume expands to 7 liters, what will the new pressure be? Highlighting my known variables and pulling them out, I know my initial volume is 5 liters. My initial pressure is 107 kilopascals. My initial temperature is negative 50 degrees Celsius, but my temperatures always need to be in Kelvin, so I'm just going to convert it right away by adding 273. My final temperature is 102 degrees Celsius, which I know needs to be converted into Kelvin, so I'm just going to convert it right away, again by adding 273. I know my final volume is 7 liters, and my unknown is going to be my final pressure, and it will be in kilopascals because the units need to be the same on both sides. I can plug all those variables into the combined gas law equation. Should look something like this. And I can solve for P2, which would require you to cross multiply and divide. So you should do 107 times 5 times 375 divided by 223 times 7. And that should get you P2. So please plug that into your calculator to make sure you're plugging it in correctly. And make sure you can get a P2 value of 129 kilopascals. Sig fig wise, all my numbers again have 3 total sig figs, so my answer will also have 3 total sig figs. Now to check this one, it's a little trickier because we know that pressure and volume are inversely related. And we see that volume is increasing, so we would think in our minds, right, pressure should decrease. However, because we have a third variable involved that does impact the relationship, it's not as easy as just plugging it in and or using one of the relationships and seeing if it makes sense. Because yes, although pressure and volume are inversely related, pressure is also directly proportional to temperature. And since my temperature is changing more so than my volume, my pressure should also increase because it's directly proportional to temperature. So when one increases, the other increases. So since my temperature is increasing by much more than my volume, my pressure is actually going to end up increasing, even though because the volume's increasing, you would think your temperature should, or your pressure should decrease. I don't know if that makes sense, but this one's harder to check because you have multiple relationships going on. So to check this, logically, it's difficult. You can do it, but it's more difficult. I would just plug it in mathematically and make sure that both sides equal each other. For the first check for understanding problem, I want you to pause the video, try it yourself, and then hit play when you're ready. In this one, your known variable should have been an initial volume of 400 milliliters, an initial temperature of 22 Celsius, which you should have converted into 295 Kelvin, a final temperature of 30 degrees Celsius, which you should have also converted into Kelvin, an initial pressure of 760 millimeters of mercury, because we are told that it starts from standard pressure and goes to a final pressure of 360 millimeters of mercury. So I'm using the millimeters of mercury, the standard pressure, in that unit so it matches with my other pressure. My unknown is going to be my final volume, and it will be in milliliters to make sure that my units are matching up. When I plug this into my equation, it looks something like this. We can cross multiply and divide, and you should have gotten a final volume of 867 milliliters. You should have rounded this to 3 sig figs because this number has 3 total. This one has 4 total, 3 total, 4 total, 3 total. So your answer should have 3 total because that's smaller than 4. For the second check for understanding question, I want you to hit pause, solve the problem, and then come back when you're done. For this problem, you should have found your known variables to be 10 liters for your final volume, 25 degrees Celsius for your final temperature, which you should have converted into Kelvin, a final pressure of 1 atmosphere, an initial volume of 9.4 liters, and an initial pressure of 0.886 atmospheres. And then you were solving for your initial temperature. You just plug these numbers directly into the combined gas law, checking to make sure that your units for each variable on both sides of the equation match up, which they do. Plugging your numbers into the combined gas law equation like so, and solving, you should have gotten a T1 of 281 Kelvin. And that's going to be it for this video.